Hello guys, today I'm going to discuss about the bilateral filter. This is one of the very important filters and you will see the beautiful results that we can get from the bilateral filter. So let's get started. So the first application that I'm going to tell you is image restoration. So here on the left you can see an original image and on the right there is an image with noise. So here you can see there is Gaussian noise that is added, and now we don't have the original image with us. Suppose that we don't have this image, and we just have this image, and we have to recover the original image using this image. So that is what is image restoration. So we will see how we can do this with the help of the bilateral filter. So this is another example. So this is like a real life example sort of. So here this is our original image. This one is the original image and this is the image that we have to restore. So this is with noise. So let us see how can we restore this using a bilateral filter. So if you zoom in a area this is the original image that we have, and this is the what we say the noisy image. So this is the noisy image that we have over here. So if you just what we say take a particular patch. So here I am taking a patch, and if you see the values associated to it, they will look somewhat like this. So they'll be more or less very near to each other. This is the original image that I'm talking about. So here you can see the value is 250, 255, 253. They are very near to each other because this is a quite smooth patch. All things are quite equal, like having this almost the same intensity. But on the other case, if you see this noisy image over here and if you take the same patch, then you will see that over here in the numbers matrix associated to that patch, here you will see that the numbers are quite different. So here you can see that there is 100 out of all of a sudden there is 100, because here there used to be 250, but due to some noise that 250 has changed to 100. Then there is 200, there is 150, 251, 45, 0. So there is also a 0 over here. So you can see, say suppose this particular pixel over here, suppose let me oh, so suppose if you see this particular pixel over here, so that can correspond to 0. So all of a sudden there is a black pixel, 0 corresponds to black, in this whole grid of white pixels. So here you see there is almost all white pixels, or you can say bright pixels, but all of a sudden here you can see some black pixel, here you can see some black pixels, and so on. So this is the problem that is making the image noisy. So all of a sudden there is a change, a big change, 100 to 200, there is a change of 100, 255 to 0, a change of 255. So there here you can see a lot of small changes. So in a graph point of view, if suppose I take a 2D graph, so there are very small changes that we can see. But on the other hand, if you look over here, it is more or less the same. If you look over here, it is more or less, there will be a little change somewhere, but it is more or less the same. So hence we also regard noise as high pass. So here you can see that this is a noisy image because it has a lot of high pass frequencies. So high frequencies, not high pass frequencies, high frequencies. So if suppose we have a filter that can remove these high pass frequencies and give a low pass output, then that could restore this image to this image. So that is what we have to see. We understand that now we need a sort of low pass filter which will block these high frequencies and only allow the low frequencies to get the smooth version of the image. So we want a smoother image like this than a image which is having a lot of fluctuations. So that is what we want. So we can use a Gaussian filter. So let me tell you what is a Gaussian filter. Okay, so what you can do is uh, consider a particular patch, like say consider this patch, and say I've written the values, the matrix values over here. So you can see these are the corresponding numbers that we have. So what we can do is, here you can see, suppose this is a 10. So I am going to use a filter like this, which is a Gaussian filter. So this is just an approximation of a Gaussian filter. A Gaussian filter actually looks like this. I'll talk about this in a minute. So if suppose I have a filter like this, which I can place it on this particular patch. So this is a 5 cross 5 5 cross 5 filter. So that will be placed over here and it will be applied on the middle pixel. So by applying on the middle pixel, what I mean is the value that will change is this value. This value will change. The output that I get of the filter will come over here. So what will happen is, when I put this filter over here, this 100, this thing will get multiplied to 1 by 1 by 256. This 255 will get multiplied to 4. This 253 will get multiplied to 6. This 200 will get multiplied to 4. This 150 will get multiplied to 1, and so on. So like this, all these values in the grid will get multiplied to these values in the grid, and then we'll add all the values. So by this particular operation, we get a particular answer, that is 190.2. So please understand what we are doing. We are just basically putting this element by element wise, multiplying each value and adding the result. So by this we get a 190.2 answer. So here you can see that instead of 10, this 10 will get replaced by 190.2. So here you will no longer have 10. Now you will have 190.2 over here. So you'll have 190 over here. So this is what this particular filter is doing. So you can understand why is this the case, because I am basically taking a sort of weighted average of the values that are surrounding this pixel 10. So I could have a standard low pass filter also, which is all ones, which is having equal weightage, which is giving equal weightage to every neighbor. You can have a filter like this also, which is all ones. So it is a 5 cross 5 filter which is having all ones. You can have this also. So a 5 cross 5, so a 5 cross 5 filter having all ones, so you'll be all ones over here. That also is something that you can have, but the point is that a Gaussian filter gives a better a better output. The reason being, you can see that these pixels will be more closely related to the center pixel. So since we are changing the value of the center pixel over here, so the farther you go from the center, the less they relate. So if suppose I give you an example, so say if suppose you take an pixel over here, this pixel of an eye, so the pixels that are surrounding to this pixel will have more or less the same color, because they are all belonging to the eye. But as and when you go further, so here you can see the pixels are totally changed. Here the pixels are white and here the pixels are black. So hence, as and when you go further, you need to decrease the weights. So that is precisely what the Gaussian filter is doing. You will have to decrease the weight so that you get a more better output. So that is only the reason why we are using a Gaussian filter over here. But you can use the low pass, the standard low pass filter also, and it will give okay results. So this is a sort of an approximation of a Gaussian filter. I just used this in order to explain you how the operation is going to happen. But in reality, a Gaussian filter looks like this. So it has two parameters. One is this S and the other is sigma. So and there are so how it is denoted mathematically is like this. So there is a pixel P. So the pixel P is the center pixel over here. So this pixel over here, this center pixel over here is my P. So the P over here is going to be fixed. It is the center pixel of the region. So over here the 10 was my P. Okay. Now uh, Q is every pixel in this box S. So once Q will be 100, then Q will become 255, then it will become 253, then 200, then 150, 100, 251, like this. Every pixel Q will take the value of every pixel that is in this region S. So this box is my region S. So here I have taken a 5 cross 5 box, but then you can have a box of 3 cross 3, 7 cross 7, 9 cross 9. You can have any number, any grid of box. So that is one particular. So this size of the box tells you how many pixels do you want to consider. So now suppose I'm putting this box over here. So if suppose it is a very big filter like this, then it will not work, because this is taking a lot of space. Like suppose if this is the center pixel, then you are relating this center pixel also with these pixels which are totally unrelated with this pixel. So these are totally opposite of what this pixel is. These are totally white and this is black. So you also have to see that you take a good particular window size or this region size. Also you can see that you cannot take a very small window size. If you take a very small window size, then you will not have many neighbors. So suppose if I take only say suppose 2 cross 2 image, sort of like this, then you can see only there are 3 neighbors. So it will be difficult to get an output like 190 point, or a good output basically, because here the average of these will still be low, or whenever you pass a low, basically a weighted average will be low because the numbers are low. So hence you need to decide an optimal value of the region, that is S. Next, so what we are doing is we are using a Gaussian filter over here. This is the formula of the Gaussian filter. So here what happens is 1 upon 2 pi sigma square. So this sigma square is our other parameter, which is called as variance. So this is the variance of the particular Gaussian. So this is just an approximation, that approximate Gaussian filter that I took from Wikipedia. But then you can have different Gaussian filters with respect to the variance. So if you see the Gaussian curve, it is something like this. So this variance, this is controlled by sigma square. So that is the other parameter that you can control. So if suppose the variance is very low, so it will be something like this. So in this particular case, what will happen is there will be a very less weightage to the outer pixels and quite more pixels to region surrounding the pixels, the pixel surrounding the particular center pixel. And if suppose the variance is quite low, it will be something like this, the outer curve. And then these will also have some weights. So that is about the Gaussian filter. So let us see what happens if I apply a Gaussian filter to this image. Let us see what happens. So you can see we get this sort of image. So this is a quite okay image, because you can see that these noise have been removed to a certain extent. You can see that this image has become smooth. But there is this other problem that we are facing. The problem is that the edges are also blurred. So you are getting an view of a blurred image. You see that this is a blurred image. It is not very sharp. That you can see that suppose if you consider this particular part, if you if you just see this part over here and this part over here, so here you can see that here this particular thing is very sharp, but here that is not the case. So more nicely, if you zoom into this, so if you see this particular eye over here and if you see the same eye over here, you can see the difference. This is blurred so much, it has been averaged, because the Gaussian filter does not know whether it is a noise that it is blurring or it is the edges that he is blurring. So the Gaussian filter has this problem that it blurs both the edges and the noise. So it blurs the noise, which is a good thing. So you can see that this particular output is very nice. If you compare these two regions over here, you can see that this is very nice, but it is also blurring the edges. So now we want something that will not blur the edges. This should not be blurred and it should just blur this noise. So that is precisely what the bilateral filter is going to do. So let us see what the bilateral filter is doing. So in bilateral filter we have using two Gaussian filters. So if you remember in the previous case where I just discussed the Gaussian filter, so here there was only one Gaussian filter that I am using, and that is based on the distance. So that is p minus q. So p is telling me the position. Also please, I forgot to tell you, p is not the value, p is not this 10, p is the position over here. So this particular position, that is say some 100 comma 100, that position, the vector position is p. It is a vector. P is a vector over here. Similarly q is the vector position of this particular other pixels. So p and q are vectors, please note that. Hence we are taking a norm over here so that we can get a scalar value. Okay, so here you can see that it is only one Gaussian filter. But in the bilateral filter case, here you can see that there are two Gaussians and they are multiplied to each other. So now we are not only having the weights in the region. So that is, I am not only considering the regions. Suppose if I take this 200 pixel as my center point. So if suppose this I am applying a filter over here, initially I was not looking up on the values. If this is 253, what you should do. If this is 11, what you should do. I'm just taking a weighted average of all these values, irrespective of what are the values actually present over here. But here what I'm going to do is I'm also going to consider the values that are associated with it. So ip is uh, 200. So ip will be actually 200. It is a scalar and it is telling you the pixel intensity at that particular point. And iq is also a scalar which will once be 100, then 255, 253, and this too. Okay, so if you see this particular example that I have taken, so here you can see that here the values are more or less quite greater. So 253, 255, 100, so these values are quite big, and these values are quite small. So you can figure out that there is an edge over here. You can see that here the values are very high and here the values are very low. Also because of noise there are some values that have become high, but more or less you can figure out that there is an edge over here. So if suppose here you can see that 200 is my center pixel. So now you can see that this 200 is closely related to these pixels. So in the picture, if you can see, if suppose I have this particular patch, so say this these numbers belong to this particular patch, and 200 is somewhere over here. This is the central pixel that we have. So now you can see that this 200 is actually related to these bunch of pixels and it is not related to this pixel. So these black pixels have nothing to do with this 200, but these white pixels have something to do with the 200. So I want that 200 should be an average of these fellows over here, and you should have no sort of um, existence of these values in the filter of 200. So that is what the bilateral filter is going to do. So if you see the case over here, so what it is going to do is, it is not only going to see the regional difference, it is also going to see the pixel difference. So this particular g theta s, g sigma s, this is the old Gaussian filter that we saw previously. So here you can see that suppose this 100, when I put the filter over here, this 100 will get multiplied to 1. That is what is happening over here. So the 100 is this IQ, the value of IQ. So please don't confuse between what is IP, IQ and P. P are the coordinates. P and Q are the coordinates. So say in this case, P will be some say 3 comma 3. So P is a vector, that is 3 comma 3 over here, and Q over here is also, so for the case of 100, Q is say 1 comma 1. So this is 1 1 1 comma 1. But IP, so IP tells you what is the pixel value at 3 comma 3, so that is 200. So IP is 200. So hence you can see that there is no norm or something over here. Here there is no this double bracket. So these double brackets are only for vectors, that is a norm. So it is the distance. So root of 3 minus 1 the whole square plus 3 minus 1 the whole square, the distance formula. So that is what this norm is telling you about. And IP and IQ are the corresponding pixel values. So there is 200 and here there will be 100. So IP is 200, IQ is 100. So IP minus IQ makes it 100. So here this is going into another Gaussian, that is so here this curve that I've drawn over here, so that is going into this Gaussian. And so what is happening is, see for the first case IP minus IQ is 100, 200 minus 100 is 100. So G of 100 will be somewhere over here. So this is 100. So this particular number, this value is going to come over here, G of 100. So you can see that say 200 minus 100 is having a huge distance, that is 100. So this particular weight is going to get multiplied over here. Similarly 4 into 255, so here 4 is because of this 4, then 255, and this is going to get multiplied by G55 because it is 200 minus 255, so that is coming over here. So here suppose there is 55. So here you can see that this is going to get multiplied by a higher weight. So when the pixel values are near to each other, so you can see that 255 minus 200 is a small value, so that is 55. So these two are near to each other, so that are going to get multiplied with a greater weight because this value is going to be higher. But if you consider a case like this, say 212, if you consider the last pixel, so here you can see that the difference between them is 188. So other things will be the same. This will get multiplied by 1 and it will get multiplied by 12. So IQ is 12, so that is a 12 over here, and this one is because of this particular thing, this filter. So this is okay, but then this G of 188, this will lie somewhere over here, G of 188. So this is a very small value which is very close to 0. So it will not, so basically if suppose G88 is very close to 0, so it will basically this effect is gone because it is multiplied by 0. Similarly over here, which is this pixel, so this pixel over here. So this is in the corner, so this is 1 into 12 into again G88, so this effect is also just gone because of this 0 over here. Similarly over here, say here I have 4 into 10, so it is this, so it is 190, so this will again approximately be equal to 0, so this effect will also go. So you can see that over here these 10, 12, this 12 and all these particular pixels are not going to have so much effect because of this G term. If the difference between IP minus IQ is very high, so if suppose here there is a totally black and here there is totally white, so the difference between the pixel values will be very high, and because of this what will happen is the weights will turn to 0 and that will have no effect over this. So these will not get averaged, and that is what we want. So please go through this once, uh, working with it, so you can work with this filter using these numbers. So just write them down once and you will understand how bilateral filter is working. So now that we have gone through the working, I'll show you some results which are very nice results. So here you can see that so here you can see this was our noisy output. This noisy image has been converted to a quite good image by the bilateral filter. So you can see that these particular things still have some noise, but that is just because they are at the edges. So bilateral filter does not blur at the edges, but it just blurs where there are no edges. So that is the beauty of the bilateral filter, and you can see that this is quite a nice output. Like you can see that if you see the patch over here, this patch over here, if you see, and if you see the patch over here, it is so nice. Here things are quite smooth, and here it is very noisy. If you see the neck, if you see this neck region over here, and if you see the neck region over here, you can understand the difference. So that is the beauty of the bilateral filter. Also, you can use bilateral filter for image enhancement. So here this is an original image, a color image, and here it is not noisy, it is the original image, it is a nice image. But if I pass this through a bilateral filter, I get this output. So you can see that subjectively, one can say that this is a nice image. You can see the texture of the hair is so nice over here. If you see this hair, it does not look that nice as this particular. It is subjective, obviously. So you can see that you can also enhance images using the bilateral filter over here. Also, if suppose you apply bilateral filter 2 or 3 times, so here I have applied the bilateral filter 2 times. So here you can see this image has become like this. So it is giving some sort of digital painting. So here you can see that this, if you zoom this part, so this particular original image has now become like this. So it looks like you have painted, somebody has done a painting over here. So you can use bilateral filter for converting an original filter original image to a painting. So you can see the beauty of the hair over here, also the texture, that It is like these brush strokes, the brush strokes that a painter does, the same can be seen over here. So it is actually what a painter might give you the output. So if in case you want to convert your original images to image that look like painting, this is what you need. So here I have used bilateral filter twice. We will see the code of this. So I'm going to, in the next video, I'm going to show you how to code this in Matlab and get this fantastic results. Also here you can see the same thing. There is this image over here, and I have applied bilateral filter twice, and you get this image over here. So you can see that it is looking like a painting. You can see the hair over here. You can see this particular region over here. This region over here is so sharp, but here it is quite realistic. And here you can see the eye. It has smoothened out the eye, so it looks like somebody has painted a color over here, but that is not the case over here, because this has a lot of detailing which makes it look real, but here it looks like a painting in nature. So if you see this original image and you compare it with the output of the bilateral filter, so this is again, I've applied bilateral filter twice. So I'll tell you why we do twice, thrice. So that is just to uh, remove these intricate details which make it look real. So here you can see the water, and here you can see the water. So there's so much difference here. There are very small details in the water which makes it look realistic. But I have removed those details, and this looks like a painting. So that was about the bilateral filter. So in the next video, I am going to show you the code, how to code a bilateral filter using Matlab, and then you can also get these fantastic results in your computer. So thank you so much for watching this video. Thank you so much.